Hey everyone, welcome back to Real Analysis 1. This will be part B of lecture 2. So where we left off, we had just identified a set which has a we had just identified a set that has an upper bound but no maximum element. So we're going to be taking off from that concept. So what we want to do next is we want to define a least upper bound. Okay, so we'll start with the definition here of the least upper bound. So let's let E be a non-empty subset of R we'll let E be a non-empty subset of R that is bounded above. Okay, so we'll start with a set E that's bounded above. So we know what it means for it to be bounded above. An element alpha, so this is an element of the real numbers, a real number alpha, is called a least upper bound. So it's called a least upper bound of E if two things. So the first thing, so in order for alpha to be a least upper bound of E, alpha has to be an upper bound of E. So alpha is an upper bound of E. And secondarily, if beta is in R, if beta is a real number where beta is less than alpha, then beta is not an upper bound of E. Okay, that's what we mean by a least upper bound. So what is a least upper bound? Well, a least upper bound alpha is an upper bound of a set E if we let E be a non-empty subset of R that is bounded above, an element alpha of R is called a least upper bound of E if alpha is an upper bound. It's got to be an upper bound to be a least upper bound. That makes sense. And what makes it what gives it the qualifier least is that if beta is any other real number that's smaller than alpha, then beta is automatically not an upper bound, right? So alpha has to be an upper bound, and it has to be such that anything less than alpha is not an upper bound, right? If that's the case, then you've got a least upper bound. Now, really, for this condition 2, so for condition 2, we might equivalently say, so we could equivalently say, that alpha is less than or equal to beta for all upper bounds beta. Right? If you take the list of all possible upper bounds of E, then alpha would be the smallest one. That's an intuitive concept, right? Now, another thing that's implied here is that, if alpha exists, if there is a least upper bound, then it must be unique. So if alpha exists, then it is unique. Okay, there can't be two least upper bounds, right? Obviously, unless they're the same, right? If you have two least upper bounds, then one of them must be smaller than the other if they're not equivalent. Now, sometimes this least upper bound is, sometimes this is referred to as a supremum, right? So it's the largest. So it's an upper bound that's the smallest, and it's sometimes called the supremum. And so that's just a synonym. And so a lot of what we'll use the notation that alpha is equal to the supremum of E. Right? If you see this means that alpha is a least upper bound of E. That's how we'll denote it. We'll use this specifically, supremum of E. Okay, and just like with the upper bound definition, we could similarly define a greatest lower bound. Right, it would follow the same, it'd be the similar definition, you just have to flip some of the words around. So let E be a non-empty subset of R that is bounded below. An element alpha in R is called a greatest lower bound of E if alpha is a lower bound of E, and if beta is a real number, where beta is greater than alpha, then beta is not a lower bound of E, right? So you could do the same thing, just flip the words. Okay. Okay. Let's talk about a theorem. Let's get a theorem out here. Let's let A be a non-empty subset of R. Let A be a non-empty subset of R that is bounded above. Okay, an upper bound alpha of A is the supremum of A if and only if, for all beta less than alpha, there exists an X in A such that beta is less than X, which is less than or equal to alpha. Okay, so let's let A be a non-empty subset of R that is bounded above. An upper bound alpha of A is the supremum, is the least upper bound of A, if and only if, for all beta less than alpha, you can find an element X in A that is between beta and alpha. Okay, so that's an interesting way to characterize a least upper bound, right? If I've got a candidate alpha, well, the basic idea here is really just that if alpha is the least upper bound of A, then for every beta less than alpha, we should be able to find some X in A such that X is between beta and alpha. Okay, and notice here specifically the inequality on the upper side. So X could be equal to alpha. Okay, right, so you can think of it like this. Here's my set. Okay, here's my alpha. Right, if beta is here, then I can obviously find an X there. Right, it gets a little weirder as we move closer and closer, right? So here's my alpha, maybe my beta is here. Well, I can still find an X. Right, but what happens when they're right on top of each other, seemingly? Well, what this is saying is that if alpha is a least upper bound, then there's got to be some X between beta and alpha. Okay, let's prove this thing. Let's try to prove this theorem. Let's prove. It's actually fairly easy to prove. So it's an if and only if, so we'll have to go both directions. So we'll start one direction. Let's let alpha equal the least upper bound of A, so let alpha equal the supremum of A. Now, if beta is less than alpha, then beta is not an upper bound of A. if beta is less than alpha, then beta is not an upper bound of A. Then, if beta is not an upper bound of A, then there exists an X in A such that X is greater than beta. Okay. All right, so that's the one piece of it. Also, because alpha is an upper bound on A, we have X is less than or equal to alpha. Right? And so in the one direction, we see clearly that beta is less than X, which is less than or equal to alpha. So that's the one way. So if you start from the fact that alpha is the least upper bound, it's clear that for any beta less than alpha, this relationship holds. What about the other direction? Okay, so for the other direction, let's let alpha be an upper bound. Let's let alpha be an upper bound such that for all beta less than alpha, there exists an X in A with beta less than X less than or equal to alpha. Okay, so then what can we say? Well, then every beta is less than alpha. Right? Every beta less than alpha is obviously not an upper bound of A. Right? Every beta less than alpha is not an upper bound of A. Right? And what is that? That's just the definition of a least upper bound, right? Alpha is an upper bound, and if every beta is less than it, then alpha is equal to the least upper bound. So it's actually a very simple, it just kind of follows from the definitions. It just kind of follows from the definition of a least upper bound. Okay, perfect. And we'll use this theorem over and over, right? We'll use this idea right here a lot when we're trying to prove anything about, well, not every time, but very, very often we will use this when we're trying to prove things about least upper bounds. When we're trying to show that such and such is a least upper bound, we'll use this theorem. All right, very good. Let's take a look at some examples here. Okay. Let's recall the set we looked at earlier. Remember A, when we had A equal to 0, 1/2, 2/3, 3/4, etc. Recall this set. Right, so since 0, we said previously that 0 was a lower bound of A. So since 0 is a lower bound of A, and 0 is in A, right? 0 is a lower bound of A, and 0 is in A. Those two things together imply that 0 is equal to the infimum of A. Infimum is another name for the greatest lower bound. Call that the infimum. Okay, the infimum. And I'll write that out. I forgot to mention that. The infimum of A. So you got the supremum and the infimum. Okay. All right, and so in the case of the infimum here, it's obvious that 0 must be the greatest lower bound. There's no element that's a lower bound that's greater than 0, right? 0 is the greatest lower bound. Now, what about the least upper bound here? Well, we'll show what you maybe all suspect, having gone through some calculus, knowing a little bit about sequences like this. we'll show that the supremum here is 1. Okay, the supremum here is equal to 1. Okay, so the least upper bound is going to be 1. And you can imagine that the sequence would, if you were to take the limit of this sequence, if you were to write this as 1 minus 1 over n, such that n is a natural number, you can imagine that the limit of this sequence would be 1, right? Okay, and so that, obviously, those two concepts, the concept of the supremum in this case, and the limit of the sequence that defines this set, those two are closely connected. Now, we won't get into the nuts and bolts of all of that for a little bit yet, for a couple lectures for sure, but those two concepts are connected. Okay, so notice, let's go ahead and walk through this description, or this derivation here. Notice that 1 minus 1 over n, this guy up here, is less than 1 for all n in n, right? So for all natural numbers, there's nothing I can plug in there to make that greater than or equal to 1. So that tells us that 1 is an upper bound. It's an upper bound on the sequence 1 minus 1 over n, such that, well, we could say n equals 1 to infinity. This is some notation you may or may not be familiar with. So 1 is an upper bound on this set, basically. Okay, it's an upper bound on this set. So to show that the supremum of A is equal to 1, we need to show that if beta is a real number, beta is less than 1, then beta is not an upper bound of A. So to show that the supremum is equal to 1, we need to show that if beta is a real number, with beta less than 1, then beta is not an upper bound of A. Right? We know that 1 is an upper bound, so if everything less than 1 isn't an upper bound, then 1 must be the smallest, the least upper bound, right? That's the strategy. It's very deceptively simple strategy on the surface, but sometimes you have to write these things out. You have to be very careful. As I said, like things that are deceptively simple can be sometimes misleading or overlooked. Okay, so here's what we'll say clearly. If beta is less than or equal to 0, then beta is not an upper bound. It's not an upper bound of A. So let's consider, we'll say, just the betas between 0 and 1. Okay. Now, intuitively, okay, our intuition should tell us that there's going to exist some integer, and we'll denote it n naught, n sub 0. It's an integer, just some integer. Our intuition should confirm that there's going to exist an integer such that, well, an integer n naught such that n naught is going to be greater than 1 over 1 minus beta. Whatever that number happens to be, whatever that number happens to be, there's going to exist some integer greater than it, right? I mean, that's a very simple thing to accept, honestly. Like, no matter what, you plug in something finite, you're going to get some number. I can always find an integer larger, can't I? Of course I can. Okay, do a little bit of arithmetic on this, a little bit of algebra. And you'll see that that's going to imply that beta is less than 1 minus 1 over n naught. Okay. All right. And so what does that mean, kind of in a picture? Right, so here I've got maybe the number 1 up top here. Maybe my beta is down here, and this guy here is somewhere in this interval. We'll just put it right there. Okay. As 1 minus 1 over n naught is certainly less than 1, right? There's no positive. I'm going to say z plus here even. So there's no positive integer that I can put in here that's, there's no natural number n naught that I can plug in here to make it greater than 1, right? So this 1 minus 1 over n naught is in beta. So what I can say is that 1 minus 1 over n naught is in A. So just to kind of clean this up a little bit, since 1 minus 1 over n naught equals n naught minus 1 over n naught, right? And therefore, beta is not an upper bound on A, right? Because what have I done? I've gone and found an x between beta and my supposed supremum, right? I've gone and found one. I've found an element x that's in my set A that's between my beta, and it's generic. It's no matter what beta is, I can always find another one, right? Whatever beta you give me, I can just find a larger integer, no problem. I can find an integer larger than this and then just do the algebra, and that's my x in B that's between 1 and beta. Okay. So obviously beta is arbitrarily chosen. Here's kind of the punchline, right? Beta is arbitrarily chosen, and therefore I can repeat this exercise, ad nauseum. I can do it as long as I need to, and so that means then that the supremum of A must be 1. Now notice here, right? So that's kind of the end of the proof here, right? So notice that the infimum of A was equal to 0, which was actually in A. But the supremum of A was equal to 1, and that was not an element of A. Right, so notice that. That's key. Right, the supremum and the infimum don't have to be in the set necessarily. Right? If they are in the set, it's usually real easy to find them. If they're not in the set, they can be more challenging to uncover. Okay, some more examples here. For the natural numbers, the infimum is obviously 1. Is there a supremum of the natural numbers? No. There's no supremum. All right, so the supremum doesn't exist. Okay. All right, very good. Let's do one more example. Let's actually revisit. We'll do this frequently in this class. Let's revisit this set B, where B is all of the rational numbers between 0 and the square root of 2, where r is greater than 0 and r squared is less than 2. Okay. Now we're roughly, of course, talking about the interval between 0 and square root of 2. Right? I mean, rational numbers, not real numbers. There's a lot of numbers in there that aren't rational. But we're talking about the rational numbers in this interval. Now the supremum of this set is not a rational number. Okay, we can show this. Right? We know that you can imagine the least upper bound here is the square root of 2, right? And that's not a rational number. So the supremum of this set is not a rational number. Let's talk that through. Let's work through that. Let's assume that alpha equals the supremum of B, and that alpha is a rational number. Now, since alpha is rational, alpha squared cannot equal 2. So since alpha is in the rational numbers, that implies that alpha squared is not equal to 2. Now, why is that? Well, basically because we know the square root of 2 is an irrational number. Okay, since alpha is, if we assume alpha is rational, then alpha squared cannot equal 2. Right, so another way to kind of think about this is if alpha squared equals 2, then alpha equals the square root of 2, which we know is not in Q. Right, so we're not playing it 100% dumb here. We are assuming that we understand the square root of 2 is not a rational number. Okay. All right. So what we'll say is then that, alpha squared is either less than 2 or alpha squared is greater than 2. Can we do that? Well, let's see. Right, so alpha squared is less than 2 or alpha squared is greater than 2, but if alpha is in B, then since B contains no largest element, remember that, there's going to exist, since B contains no largest element, there exists a Q in B such that Q is greater than alpha. Right? But this obviously is a contradiction, right? But this contradicts the fact that alpha is an upper bound of B. Okay. Right? So if alpha squared is less than 2, then if alpha is in B, so if alpha squared is less than or equal to 2, then alpha is in B, and B contains no largest element, so there exists a Q in B such that Q is greater than alpha, right? So that's a contradiction. Well, if alpha squared is greater than 2, then there exists a Q less than alpha such that Q squared is greater than 2, right? But then Q would be an upper bound of B. But then Q would be an upper bound of B, right? Which is a contradiction of property 2. This would be a contradiction of property 2. Now, what was the property 2? Well, property 2, remember, of the least upper bound definition was that for all beta in R with beta less than alpha, then beta is not an upper bound. But here we see that would be violated. Okay. Right, and so if alpha squared can't be less than 2 and alpha squared can't be greater than 2, then obviously alpha squared has to equal 2. Okay. And so that implies that the square root of 2 is equal to the supremum of B in this sense. And so the least upper bound of B is not a rational number. right? Even though B is a set of rational numbers, it has a least upper bound that's outside of the rationals. Okay. All right. Very good. Okay. So this has all been kind of, I know this is a longer lecture for sure, but this has all been kind of preliminary material for the least upper bound property, right? So we've defined what we mean by a bounded set. We've defined what we mean by a least upper bound. And now we need to talk about the least upper bound property. So let's talk next about the least upper bound property of R, of the real numbers. Okay. So the least upper bound property is also frequently referred to as the quote-unquote completeness property of the real numbers. So the least upper bound property is also called the completeness property of the real numbers. And as we go forward, we'll kind of see why that is a bit more. And really, I mean, it is really the foundation of many of the ideas that we'll work through in this course. It's this completeness concept of the real numbers that makes real analysis so interesting. And so here's what it says. And you may look on this and say, okay, well, that's profound. We'll see. But basically, the least upper bound property of the real number says that every non-empty subset of the real numbers that is bounded above has a supremum. Well, so I should say every non-empty subset of R that is bounded above, and you could an analogous statement could be made for the subsets that are bounded below. So bounded above, or we'll say below in parentheses, has a supremum, or infimum, depending on the case, in the real numbers. That's the key, right? So the previous example, we saw a subset of the rational numbers that had a supremum, but not a supremum in Q, right? To find the least upper bound of our set B from the previous example, we had to go outside of the rational numbers. We had to look at the square root of 2. Square root of 2 is not a rational number. But what the least upper bound property for the real number says is that no matter what, if you're dealing with a subset of R and it's bounded above, it's going to have a least upper bound, a supremum, in R. I will never have to go outside of the real numbers to find a least upper bound for a real number subset. There's a special thing about the real numbers which makes it complete. Now we'll kind of proceed with this property as though it's an assumption or an axiom, but it is actually something that's been proven. You could go look at the proofs of the least upper bound property. There are proofs. There are several different ways to prove it. There's proofs by Richard Dedekind, he used Dedekind cuts. We won't probably get into that here in this course, but another one would be by Georg Cantor, who used Cauchy sequences to prove that R could be constructed from Q, right? Which is another way of saying that this least upper bound property implies the least upper bound property. Okay. All right. Very good. Okay. Let's go ahead and take a look at an example. Let's take a look at an example here. For this example, we're going to kind of prove something a little different. So we wish to show that for every y greater than 0, every real number, so we'll say y is in R, for every real number greater than 0, we wish to show that there exists a unique alpha positive. There exists a unique positive alpha such that alpha squared is equal to y. Okay, so this is going to be an interesting proof, right? So what we're trying to show is that every real number greater than 0 has a square root. Okay. So we're just trying to show that every real number y greater than 0 has a square root. Okay, so just put a little plain English on there, right? So every real number y greater than or equal to 0 has a square root, and we should write it so alpha would be equal to the square root of y. Okay, so let's actually narrow this down a little further. Let's just look at the y's greater than 1. All right, we'll actually narrow it down just a little tighter. All right, so let's start with a set. Let's let C equal the set of x, real numbers x, such that x is greater than 0, and x squared is less than y. Okay. All right, so this is a set that, we're talking about all of the sets. I mean, this is going to be kind of run parallel to really the example that we previously saw, right? Like all of the r's in Q such that r is greater than 0 and r squared is less than 2. But here we're doing it more general. In a more general sense, this set C is kind of more generally defined, right? Y is a variable, right? It's a general number. And also, importantly, x is no longer a rational number, right? So x, in this case, is a real number. Big difference, right? So if we think of y equals 2, then this set C is basically similar to the set B that we saw before. So if y equals 2, this set C is like the set B from previous examples. Right, big difference here is that here we are talking about R, X in R, and before it was X in Q. Okay, so kind of a big difference there, but just make sure to point that out. Okay, so let's talk this through. Let's see what happens here. All right, so since y is greater than 1, 1 is going to be in C, and we can say then that C is non-empty. Okay. All right. Also, since y is greater than 1, we know that y squared is greater than y, right? And therefore, we could say that y is an upper bound on C. Okay, so hopefully that should follow. Okay. All right, then by the least upper bound property, C has a supremum in R. It has a real, there exists a real number which is the least upper bound of C. So let's let alpha equal this number. Let's let alpha equal the least upper bound of C, the supremum of C. And from this we can show, from this we will show that alpha squared equals y. Okay. Now this is going to run really similar to the proof that we saw previously with the real numbers, except it's going to actually be a little bit cleaner. Okay, so we'll construct a real number b, or beta, and use it to derive a contradiction. Okay, so let's do this quick. So let's let beta be constructed as so how are we going to set this up? So we'll say beta is equal to alpha plus y minus alpha squared over alpha plus y. So really similar to what we did before. I think before we would have said p plus 2 minus p squared over p plus 2. All right, so we can run really the same algebra on this, and we'll have alpha plus y minus alpha squared over alpha plus y. Right, and that's all going to be equal to y times, and I'm abbreviating a few steps here, y times alpha plus 1 over alpha plus y. And I'm going to denote that as 1. We're going to come back to that. And now, similar to before, we're going to consider beta squared minus y, right? Before we would have said p squared minus 2, right? And so we're going to do something similar here. So consider beta squared minus y. Okay, so beta squared minus y will be equal to basically this thing, y times alpha plus 1 over alpha plus y squared minus y. Okay, and I'm not going to go through the whole derivation here, but I'll let you guys do it. You can see, you can just run through, just expand this thing, collect terms, simplify, etc. And you can see that this is equal to y times y minus 1 times alpha squared minus y over alpha plus y squared. Okay. All right, and so let's assume first, we're going to kind of combine the previous couple of big examples. So we know that we think alpha squared equals y, but we're going to assume that alpha squared is less than y first, and see that in order to show that alpha squared is equal to y, we're going to assume first that alpha squared is less than y, and then we're going to show that that derives a contradiction. Then we're going to assume that alpha squared is greater than y and show that that produces a contradiction. The only thing left will be that alpha squared equals y. So if alpha squared is less than y, well, what we're really saying there is alpha squared is not equal to y. Starting with that, right? So alpha squared is less than y, so it's not equal to y, key. Then from this guy, we'll call this 2. Sorry about that. We'll call this 2. From 1, we can see that beta is greater than alpha. Okay, since y? Since beta equals alpha plus y minus alpha squared over alpha plus y. This thing on the top is not positive. This thing on the bottom is positive. Right? Double check that you can see why that's the case. Right? This top value is not in P, the bottom value is in P, and so the whole thing is not in P. Right? So that means beta is greater than alpha. And from 2, we get beta squared is less than y. And why is that? Well, what we've written here is that beta squared, sorry about that, let me scooch up here. So beta squared is less than y. From 2, we can see that beta squared is less than y. And we would say that's because, and what did we get for beta squared minus y? We had y times y minus 1 times alpha squared minus y all over alpha plus y squared. Now, y is in P. Y minus 1 is in P. Alpha squared minus y, that's not going to be in P. Okay. And alpha plus y, of course, that thing squared would be in P. So this whole thing is also not in P, right? And so the implication there is that beta squared minus y is less than 0, so beta squared is less than y, right, as we've written here. Okay, so I've got beta is greater than alpha, and I've also got beta squared is less than y. This produces a contradiction. This produces a contradiction. Why is it a contradiction? Well, beta is in C, right? And how do we know it's in C? Well, beta squared is less than y, right? And beta is greater than alpha, which is the supremum of C. Well, that can't be true, right? So clearly, I mean, you can't have beta be in C and also greater than the least upper bound of C. So clearly, alpha squared less than y is not true. Okay, and so this all kind of comes from us assuming here. Well, let's go the other direction then. Right? Let's see what happens if we do it the other way. On the other hand, if we let alpha squared be greater than y, then what do we get? Well, from 1, we get that beta is less than alpha. Right? Why is that? Well, let's write this all out again. Since, what did we have? We had beta equals alpha plus y minus alpha squared over alpha plus y. Kind of looking back here. The top here is not in P, right? The bottom is in P, so this whole thing is not in P. Okay, and so that means beta minus alpha is less than 0. Right, so beta is less than alpha. Okay, and from 2, we see that beta squared is greater than y. Right? Why do we get that? Let's see. Well, beta squared minus y, we said that that was y times y minus 1 times alpha squared minus y all over alpha plus y squared, right? Y is in P, y minus 1 is in P, alpha squared minus y is in P, alpha plus y quantity squared is in P, so this whole thing is in P, right? And that implies, of course, that beta squared minus y is greater than 0, which is where you get that beta squared is greater than y. Okay, but then, right, if beta squared is greater than y, it must be an upper bound on C, right? It's an upper bound on C. We already said y is an upper bound on C. But this is going to imply a contradiction since alpha is equal to the supremum of C. Right? If alpha is the supremum of C, beta can't be less than alpha and also be an upper bound of C. Okay, right? So if alpha squared is not less than y and alpha squared is not greater than y, then alpha squared must equal y. Okay. And so there we go. So the, unraveling all of that basically implies then that, implies the result that we were after, right? Implies namely that every real number y greater than 0, we could create this set C for it, and we've used this set C to show that alpha must be equal to the square root of y. Alpha being the supremum of the set C must be equal to the square root of y, and so a square root of y exists for every real number. Okay. Now notice, right, this argument definitely does not work if we're dealing with the previous set B. This does not work with the set B, where B is all rational numbers, where r is greater than 0 and r squared is less than 2. That, it doesn't work there, right? Right, and I mean, it doesn't work because, for a couple of reasons, right? Really it doesn't, I guess the main reason it doesn't work is because beta, as we've defined it in the proof above, may not be in Q. And therefore not in B, right? So so that's kind of the main reason it doesn't work. Okay, but ultimately, really the idea we're trying to draw out here is that it doesn't work because B does not have a least upper bound in Q, right? So B does not have a supremum in the rational numbers. Okay. All right. Very good. So this is actually going to be a 3-part lecture. So I'm going to end part B, with that. And when we pick up in part C, we'll talk through some ideas about intervals, and then we'll look at some consequences of the least upper bound property of the real numbers, and we'll visit some previous some interesting theorems that you may have heard of, things like the Archimedean property, and others that can be proven if we start from the standpoint of the least upper bound property. All right, so we'll end here with part B, and then part C we'll pick up right where we've just left off.